Now, starting with the third video on rotational motion, we are trying to derive a relation between the torque and angular acceleration. Now, in the process of deriving the relation between the torque and the angular acceleration, we will find out what is meant by this term moment of inertia. Now, suppose we all know that when a force is applied on a body, a linear acceleration is produced in the body. Similarly, when a torque is applied on a body, an angular acceleration is produced in it. So it can be said that the torque plays the same role in rotational motion as that of force in the case of linear motion. That means torque in case of rotational motion and force in case of linear motion has the same role. Now that is why torque is known as the rotational analog of force. So you can write here the torque is the rotational analog of force, because these two equations, F is equal to ma and tau is equal to I alpha, are same. This I is known as the moment of inertia, which we will be deriving when trying to finding out the relation between the torque and angular acceleration. So this is the relation we are going to prove. Tau is equal to I alpha. Now for that we take a body, suppose PQR, comprised of masses M1, M2, M3. Suppose this is M1, M2, M3. From the fixed axis, the distances are R1, R2, R3, etc. Now this is rotating with the angular velocity of omega around the axis AB. Suppose the name of the axis is AB. Now this PQR body will have the same angular acceleration because in case of pure rotation, the axis of rotation remains fixed and the angular acceleration of each of these point masses remains the same, but due to the difference of distances, or rather the difference in distances of the point masses from the axis of rotation, the linear accelerations are different. So the force acting on M1, suppose the force acting on M1 is equal to force into acceleration. That means F1 is equal to M1 A1. Now similarly, force acting on M2 will be F2 is equal to M2 A2. I have already stated that the linear accelerations will be different. Now we can replace this A1 by R1 alpha. The relation between the linear acceleration and the angular acceleration is A1 is equal to R1 alpha. Now the force F1 you can write here M1 R1 alpha, here M2 R2 alpha, and similarly for the third case, and so on for n number of cases. We can write it as Mn, Rn and alpha. Now the torque relating to this force, torque or the moment of force, torque due to F1 about AB, or the axis of rotation, it will be equal to torque due to F1 about AB. It will be equal to F1 R1, force into perpendicular distance in the line of action of force. That is F1 to be replaced as M1 R1 alpha into R1. That becomes M1 R1 square alpha. This M1 R1 square term will be related to the moment of inertia. How? Similarly, you can find out the torque due to F2 about AB. Similarly, F2 R2. That means M2 R2 alpha and R2 again. That means M2 R2 square alpha. So similarly, for any number of bodies, any number or n number, we can write of bodies, we can write the torque to be M1 R1 square alpha plus M2 R2 square alpha plus dot dot dot. That means we can take alpha common from this, and this summation expression can be replaced by a single expression like this: mi ri square I is equal to 1 to n, or suppose 1 to 4, 1 to 5, the number of particles in the system, into alpha. Replace this large term by I, that is I alpha. So what is I? So I is equal to summation of mi ri square I. So this is known as the moment of inertia of the body. This is known as the moment of inertia of body. Moment of inertia of the body about axis of rotation. Now the axis of rotation was AB. So this is moment of inertia of the body about the axis of rotation, that was AB. So we can write or define torque as moment of inertia. So tau will be equal to I into alpha. So this is the formula for torque when we are relating it to the rotational motion. This is the relation between torque and angular acceleration. Also here you can write in the vectorial form also. Now torque is an actual vector. Whatever vectors we are relating to in the rotational part will always be actual vectors. That means angular velocity, acceleration, torque will all be axial vectors because they always direct along the axis of rotation. That means we can write in the integration form also. In calculus we can write. In calculus, or we can write continuous bodies. That means bodies which have continuous masses. We can write it as I is equal to r square dm. That means a small amount of mass dm from the axis, the distance is r. This is dm, this is the axis. The moment of inertia of this small mass dm with respect to the axis AB or the rotation axis is r square into dm as m ri square. So m r square. Now the unit of I, what will be the unit of I? The formula is m r square. So m means kg and r square is meter square, and this is for SI, and for CGS we can write it as gram centimeter square CGS. The dimension will be ml square, mr square, so ml square, the dimension will be ml square. Now a little bit of more discussions about the moment of inertia. So some important points about moment of inertia. Now first one is moment of inertia depends on the mass distribution of the body. Mass distribution of body. Now a little bit of more explanation. It says that moment of inertia not only depends, the moment of inertia term means I is equal to mr square. So it not only depends on the mass of the body but also depends on the distance of the particles constituting the body from the axis of rotation. That is, indirectly we can call it as the distribution of mass or mass distribution of the body. Now second point we can write that moment of inertia, this is a very very important point. Moment of inertia is the rotational analog of mass. That means the role of mass in linear system is same as the role of moment of inertia in the rotational system. Now as torque is the rotational analog of force, so we can also tell that mass and moment of inertia are analogues of each other. So moment of inertia is the rotational analog of mass. The third point, moment of inertia, is it a scalar or a vector? It is neither a scalar nor a vector. It is neither a scalar nor a vector. It is actually a tensor. It is a tensor. That means I cannot describe tensor as a whole here. I can only say that tensor is something. The first kind of tensor is a scalar. The second kind of tensor is a vector. So tensor is something that is neither a scalar nor a vector. But for the considerations of this chapter, according to the considerations of this chapter, we will take, according to the considerations of this chapter, we will consider moment of inertia to be a scalar quantity. Because m is scalar and r square, as there is a square term here, so we can call this as a scalar quantity. But after this class 12, when you reach the honor stage, you will find out the moment of inertia is an example of a tensor, pure tensor. Now a little bit of more discussion about this point number 2, that is moment of inertia is a rotational analog of mass. Now from the expression wise we have already understood that it is analog of mass, rotational analog of mass. But the role played by mass, now what is mass? It is a measure of inertia, or rather translational inertia. Mass is a measure of translational inertia. Now this term inertia, what does this mean? This means that inertia is a type of hindrance. We can tell inertia to be a type of hindrance that a body shows, that is generated in the body to resist any change in its translation motion. It is a hindrance to change in translational motion. So mass is a measure of translational inertia. What does inertia means? Translation inertia means it is a hindrance to change in translational motion. That means a body in rest tries to be in a state of rest. That means if we try to move the body, it will always try to be in a state of rest. That means it is hindering the change. Always, if we consider the moment of inertia, now what does this moment of inertia means? In absence of external torque, the body either remains at rest or executes uniform circular motion. That means the moment of inertia of the body can be called rotational inertia. So moment of inertia can be called rotational inertia or inertia of rotation. Now what does this term rotational inertia means? Similar explanation can be given here as well. We can tell rotational inertia means it is also a kind of hindrance. It is also a kind of hindrance, but to a change in rotational motion and not translational motion. Hindrance to change in rotational motion. To sum up, it can be said that the relation between moment of force or torque and the moment of inertia is similar to the relation between force and mass. So moment of inertia plays the same role in rotational motion as played by mass in translational motion. I hope it is clear to you. Okay, now I will be forwarding you a chart of moment of inertia of some uniform bodies of mass m, suppose like a rod, circular ring, etc. The proof of all this will not come in your examination, but I will be making a video on those proofs of the evaluation of the values of moment of inertia in a separate video that is required for joint entrance and not regular CBSE. But one more term I have to describe here, that is radius of gyration. Sometimes it is also called by some people as radius of gyration. Now, what is radius of gyration or gyration as you called it? Now, if we take a rod, we have to take the axis here, we are taking the axis here, it doesn't matter. For radius of gyration, we mean that this rod can be converted to a single point mass. Suppose the point mass is m. That means the total mass of this rod was m. I have taken a point mass of m. That means the rod has been condensed to a single point of mass m. Now, if this mass is separated from the axis of rotation by a distance of k, we can write I is equal to square root of k, but first I must write is m is equal to mr square, mk square is equal to I. From this we can get k square is equal to I by m, and k is equal to square root of I by m. I will be discussing this again later.